Okay, we're gonna start with lecture in a second here, so I don't know how you guys want to get set up. All right. So today we're going to be looking at user authentication. You guys had a bit of a lecture on user authentication before, looking at things like the authentication that you use for TinyApp. We're going to do a little bit more of a deep dive today. User authentication is a huge topic. People spend whole careers looking into it. So we're not going to go as deep as we can, but we're going to get a little more nitty-gritty on authentication. So what have we done so far? Can anyone give a bit of a summary on some of the things we've used to authenticate users on the apps and projects that we've had up to this point? Yeah, so we use cookies. What else? Sessions. Cool. Anything else? Encryption. Yeah, we use like bcrypt as a library. Why were we using bcrypt? To save passwords. Yeah. So we stored passwords and sensitive data with bcrypt. We used hashes. And we mentioned some of these things here. We use cookies, sessions to identify someone or to authenticate someone. Was there a good understanding on the difference between sessions and cookies? What did we understand the difference between those two were? Yeah, cookies, there's a few differences, but one of the main ones is cookies are stored client-side, sessions are stored server-side. I think it also mentioned sessions have a expiry date, so they'll only last a certain amount of time. With sessions, you still store something client-side, but it's just a key or just a token to identify where on the server side their session is stored, but none of the actual information. So if you're trying to store an email and an ID, it only ever stays on the server. Cool. So we've got like kind of a good set of tools right now, but there's definitely more to authentication than what we have so far. Just to start off, I think we can clarify a couple of terms that are similar and easily to get confused. So we have this idea of authentication versus authorization. They're used in tandem a lot of the time, but they mean different things. And you can get one right and the other wrong, or vice versa. So authentication is confirming your identity. It's proving that you're a specific user. So when you're logging into your site and you're providing your credentials as email and password, that's a process of authentication. If I'm correctly authenticated, then when I sign into my email, it knows who I am, and it knows that I'm a registered user, any additional information that it may have about me. Authorization is the process of granting, it should be here like correct access. So you verify that you have the right authority to access, see, or get something. So if I'm on my Facebook page or something, if I am myself, I have the ability to like add photos, edit my page, do stuff like that. I've been given more authorization than if you were to look at my Facebook page. Authorization is another thing we have to think about. Are we consistent with our authorization across our application so that some base user isn't all of a sudden given all these admin privileges and can run wild on our applications? So they're two separate things. They obviously overlap and use each other, but authentication is confirming who you are, whereas authorization is getting the correct access depending on who you are. The other two terms that are pretty similar to each other is encoded and encrypted. Encoded, they both, even to like looking at something that's encoded or looking at something that's encrypted, they can look very similar as well. So encoded is when you're transforming data into another format. You're using a scheme that is somewhat available, and can easily be reversed. The purpose when you're encoding something isn't to hide what the data is, it's just to make it more usable. It's to put it into a format that maybe a programming language can use better, maybe the other person who's using it can understand it easier. Whereas encryption is transforming the data so that it's secret. It's using a format so that only specific individuals can reverse the information. And the purpose is to obscure data. So if I encode a string and I encrypt it, it might look similar. They might both be like non-human readable to myself just looking at it. But the difference is kind of in the purpose. The encoded thing, when you encode something, you want people to be able to reverse it back into a usable state. Whereas when you encrypt things, you don't want people to be able to read it unless they're a specific person that you've given either a key or a specific way of decoding it. Does that kind of clarify the difference between those two? The other thing is, you can have like a bad encryption, and we'll look at that in a bit. So the main difference we're going to focus on right now is purpose. So if my purpose is to hide the data from other people, we're going to call it an encryption. If my purpose is to make the data more usable, we're going to call it encoded. So how do we encrypt things? So far, we've used bcrypt, which is an algorithm that was like provided for us. Well, actually, bcrypt, we'll look at it a bit more, but it might not be encryption in the truest sense that we're thinking about. Any thoughts on how we encrypt things? Rainbow table. Yeah, that's an encryption. So what's a rainbow table? So we're going to do a bit of an activity. Does anyone want to volunteer as our cipher? Okay. So this is, don't show this to anyone.
Okay.
That has what you're going to transform. We're just using numbers to keep it simple.
Okay.
And so each screen we have a set of numbers, and I just want you to decode what these numbers mean. Using the using that, yeah. Sure, and then let us know. And we're gonna see if anyone else can guess what the pattern is as we're getting it. So this can be thought of as we have this secret communication link, and you guys are all just outside observers who we don't want to share the encryption. And if we can communicate successfully back and forth without you guys knowing, then we have a good encryption going. Okay, so what is it? Yeah. Yeah, so this doesn't make sense, but when we decrypt it, maybe it's a date. It's like Halloween. Okay, what about this one? So we'll meet at 107. Anyone close to figuring it out? No? Maybe. So this last one, just the numbers. If you know what it is, you can try and beat him to the punch if you want. Yeah. Yeah. So we had this kind of not very hidden message, but we got additional information from the stuff that we had just in white. Let's see. So we were just doing a shift here. Mm. So we had 0 being shifted to 5, 1 being, and vice versa. This is just kind of like mod 5 also. So we're just adding 5 onto the number modular 9 so that it would roll back over. This is an example of, or an adaptation, not really an example of route 13, which is a form of encryption. So with route 13, you use the full alphabet, and you can split it on a letter. So here we're splitting on M, and you just switch letters back and forth. So like the word hello would then be Uribe. This is part of a broader type of ciphers or encryptions called Caesar ciphers that was actually used by Caesar way back in the day. Him and his like military commanders would use different route 13 or different kind of like floating window ciphers like this to just encode communications or encrypt communications that they had between each other. This would obviously be harder to decode than our simple number one, given the wider range of values. And when people are using route 13, they shift the window that they're splitting it by. So we're starting at A, and we're going 13 letters, and then we're doing the second 13 set of letters as the corresponding one. You could start at B and then do your shifting there and split it. You can start at different letters and alter. People would even do rotating route 13 schemes. So they're saying like, hey, we're going to do the E version for this message. The next message, we're going to do the H version, back and forth. But what are some problems with this encryption right now, or even the one that we were doing beforehand? Yeah, the algorithm's too simple. It's pretty predictable. What are some other problems, even if we were using like the route 13 one with all the letters? Yeah, yeah. It's always going to look like words. These are all things that make it kind of weak. You can eventually see the pattern over time. The other thing that is actually pretty important is that in order to do this encryption, I had to physically come and pass the encryption. And if anyone had like seen the paper or like intercepted it on the way, then our encryption's ruined, even if it was a highly or a more complex encryption. One of the problems with encryption is that I need to communicate with the person I want to be sharing secret messages with what the encryption is. And that communication, because we don't have an encryption set up at that point, is inherently like vulnerable. If we don't have a secret way to communicate, how can I communicate the new encryption secretly? So that's maybe one of the vulnerabilities that we're going to look at today. There's also a bunch of vulnerabilities when we're thinking about security with our web applications, whether it be authentication or otherwise. So this is kind of some of the areas. You can have vulnerabilities in transit. So in transit being, we now know that our web applications have a client and server and multiple people connecting and communicating over a network. During those communications, we can have vulnerabilities. We can have packet sniffing. Packet sniffing is like information's physically being transferred over, say, a wire or over Wi-Fi. If we have a device that's there that can intercept the Wi-Fi signals, intercept maybe even the physical zeros and ones along a wire, and they know how that data is being transmitted, they can then interpret that and see what's happening. We have spoofing. So spoofing is the idea of impersonating another user. If I'm doing HTTP requests from my computer to another server, someone could impersonate that server, pretend that they're the correct people to be sending me information back and forth. You can just have like good old-fashioned data breaches, data stored physically on your computer. If I come and steal your computer, maybe I have access to some of your data. There's also like brute force things with passwords and security. Computers are day by day being faster and faster at just trying millions upon millions of combinations. You can brute force your way into something that's secure just by trying enough combinations in theory. We can also, sometimes the greatest security flaw is just ourselves. We can willingly give up data and sensitive things without knowing it. The social engineering, the idea of social engineering is, how do I contrive a social situation where I can elicit sensitive information from someone? So there's a whole set of kind of hacker type people who they focus on social engineering. They focus on, calling up someone and pretending that they're a user from a telephone company, and based on the way that they communicate with the agent, they can get an email from them, phone number of you. A similar way for willingly give up information is like phishing. I'm sure we've all got those like really horrible phone calls within the last year from like Canada Revenue Agency claiming that we like did some tax fraud or something. They want us to call and give them our SIN number. That's an example of phishing. So you're just throwing out as many kind of feelers as you can to try and get information from someone. Maybe you're like a African prince with a lot of money, and you're trying to get bank information so you can send money. Those are like phishing things. And then lastly, like you can impersonate someone to get even more information if any of these were successful. So to kind of work through some of the things that we need to build up for our authentication, we're going to be using a continuing example of Bob and Alice. And so Bob and Alice, they just launched a new startup. It's a web application called StringCan. StringCan is a messaging app created to send secret confidential messages from one person to another. During testing, Bob and Alice find out that some of their secret messages have appeared online. After some investigation, they find out that Sneaky Eve has been using a packet sniffer to intercept some of their sent data. So they need to solve this problem somehow. They want to make it so that the data is, if the data is intercepted, it can't easily be read. So what was our tool for maybe fixing this? Encryption. SSH has some level of encryption, if I remember. But yeah, more generally, we want to do encryption. But how do we encrypt? We saw one example with our Route 13. But in a more modern situation, we're using algorithms and keys. So a key is usually a random string that is used with an encryption algorithm to encrypt data. So you have a specific algorithm, you give it data and a random set of string or numbers, and then you have encrypted data. With a basic encryption algorithm, you then can use the same algorithm, you give it the encrypted data, and if you use the same key, you now get the original data popped out. So we can see with these two encryption and decryption equations why it's called a key. You have a single key, you can lock the data, you can decrypt it or encrypt it, and then with that same key, you can unlock the data and decrypt it. So these algorithms are created in such a way that you need to both know the algorithm that was used and know the key to decrypt it. So they're very secure. It's kind of out of scope of this lecture to maybe look at how one of these algorithms are built. But you can look into it, and if it's something you're interested in, it's not terribly complex. But yeah, it is interesting. Some examples are like Blowfish, AES. And it's not something that we're going to be like making ourselves. People come up with these algorithms, and they're publicly available so that we can take advantage of them. But they're secure in such a way that just because they're public available doesn't mean anyone can decrypt it. They still very much need a key in order to encrypt and decrypt it. So them being publicly available doesn't make them very much less secure in this case. So we can use one of these algorithms, but we still have that problem where I need to securely pass someone my key. If we're going to be, me and Carlo are going to be communicating over like AES or something, I still have to give him a key so that he can send the information to me securely, and we can do it vice versa as well. So I'm going to give you guys time over the break to think of how we might be able to do this. We've got like a bit of a demo. So we have 2 locks. Each lock has a pair of keys. I'll separate them. So this is one lock. It has a set of keys. This is a combination lock. Its keys are just the combination written on a piece of paper. And so if we have 2 persons, we have maybe Bob with their key and lock. And then over here, we have Alice with her key and lock. And we have a means of communication. So say we're using just standard post office mail. And we want to be able to set up a communication link between the one house and the other so that while this is being sent, the post office people can't look at our information. We don't trust them. Maybe they're going to be like spying on what we're saying. So there's a way of doing it with 2 sets of locks and 2 sets of keys so that me as a postman, I'm not going to be able to see what is being sent back and forth. I also got a little bit of a illustration here. So we have like Bob with his key and lock, and then Alice with her key and lock, and we have one means of communication, like this lockable box. Be creative with how you think of it. This lock, anything you can physically do with this is game. This box doesn't actually lock, so it's not the greatest prop. But for our cases, if the lock is on the handle, then you'll count it locked. So we'll take a 15-minute break, brainstorm solutions, and we'll see if we can get a way that we can have secure transport between Alice and Bob with just these constraints. We'll come back at 9:40. All right. I think we had some people crack the box key exchange thing. So maybe we could get just 2 people come up and demo it quickly one last time to yeah, if you want to come up. And yeah, do it. And one more person, and I'll just act as the postman. Okay, you could be on the side. Okay, so just walk through what you're doing.
So this is the combination log, and this is the combination. I put a combination inside the box, lock it.
You gotta like go at the angle.
Right,
I should get it. Okay, so postman, I can't unlock it because it's locked. I give it to you. Okay, it's even more locked. I can't do anything.
and I use the combination to unlock my lock.
Okay, still locked. I can't do anything.
No.
And so now they both have the key. So in this case, they don't need to use that red lock necessarily anymore. They can just use this lock to, whenever they want to send something, they're just going to lock it. And then the other person has the key, so they can unlock it. So anything they put in here now is like confidential. And yeah, good job, guys. Cool. So this is another way of what we just demonstrated, what you guys just solved, is called a Diffie-Hellman key exchange. This is another way of doing it where you both have a common key at the end. This is like harder to visualize, I think, than the key passed back and forth. But the key point here is that with any of these encryption algorithms, there's like an operation that's fast to do, counter-opposed by operation that's really slow to do. So in this case, we can combine paint colors really fast. So yellow plus orange, we get this like beige color. That's really quick to do. But color separation takes an eternity. So I can't take this beige color and then just extract orange and yellow from it. This has like a simultaneous pass at the same time. So we have this like public transport beige and public transport blue that just gets passed at the same time to each other. And then instead of having 1, 2, 3 passes, you kind of have 2. But you don't really, because this common paint, this yellow, needs to have been passed beforehand. So even with this, you have a 3-way pass. You're going to need 3 ways of communication for any version of like Diffie-Hellman that you end up doing. If you're interested in this paint one, take a look at it in the notes and stuff. I'm not going to go into too much detail because I think this is a better way of kind of understanding that key exchange. Okay, so Bob and Alice, they kind of beat even that one eventually, but it's not done yet. So after implementing encryption on StringCan messages, Alice receives the following message from Bob. Bob's like, hey, Alice, quick question. What was the name of the high school you attended? Good job on the encryption, by the way. Also, Sarah and I were just talking, and we couldn't recall your mother's maiden name. Trustful Alice responds with, hey, Bob, weird question. It was Harry Herpson High School. The encryption was hard, but now Sneaky Eve won't get our info. Oh, and tell Sarah it was Smith. Later, Alice is talking with Bob, and she brings up that weird conversation that they had over StringCan. Bob's like, I don't know what you're talking about. So they both look into it, and they find out that Sneaky Eve struck again and was spoofing Bob's IP to send fake messages. So even though the messages that they were sending between Bob and Alice were secure, no one could like intercept them and know what they were saying. Eve had struck even before then and was just pretending to be Bob. So what solution do we need? By encrypting the messages, Bob and Alice were able to ensure that all conversations were secret, but they were not able to ensure that they knew who the secret conversation was with. So there's a couple different combinations of things we can have. You can have a secret conversation with someone who you can't identify. So you know that any message you send to that person are secure, but you don't really know for sure that it's the person you think it is. You can have a public conversation where you're sure you know who the person is. So we're talking and you guys can all hear, but I know for sure that I'm talking to a specific person. Or you can have a secret conversation where you know for sure who the person is. So obviously, this last one is what we're looking for. We've only achieved this first one's level of security at this point. So in order to achieve a secret conversation where we are verified, we know who the person we're talking with is, we first need to introduce public and private keys. So the encryption method we just looked at with the box was like a symmetric key encryption or like single key encryption. So I use one key to lock my message, and then I use the same key to unlock it. With public and private, you have two sets of keys. So Alice will have a private key and a public key, and Bob has a private key and a public key. Public-private keys kind of work like a mailbox. The public key is like the location of your mailbox. So I can give that out to a bunch of people. I can say, send me some mail at this address. And the private key is like the lockbox or the key to my mailbox if I have a locked mailbox. This is assuming that like the postal service in this case is 100% secure. So I give you guys all my public key, all my mail address, and then when you send stuff, no one can read it except me because it ends up in my mailbox, and only I have the key to unlock my mailbox and check to see what you guys have sent me. An example of this is RSA, very common public and private key encryption, or they're called asymmetric encryptions. But if you think about it, we still haven't solved the problem of authenticating who sent the message. So this is public and private keys is another way to have like secure messages sent to me without necessarily doing a key exchange. I can just give you my post address. You can send me secure messages. When I open my box, I know I'm the only one who's read it up to that point. But I still don't know that it was for sure, Seth who sent me the mail. Maybe someone else wrote the name down and sent it impersonating them. But we can use this like asymmetric keys to do something called signing or to create something called a certificate. So this signing thing is used to confirm the identity of someone. It must be used with public-private asymmetric encryption. We can't do it with our single keys. And before we even look into signing, there's a fact about public-private keys that we kind of have to look at. So Bob and Alice both have a public key and a private key. If I take the public key and use RSA, which is the encryption algorithm, with a message, I get the encrypted message. And then I can use the private key plus RSA to take this encrypted message and get the decrypted message. But I can also do the reverse. So this first pair is how it's like typically used. You keep your private key private, you give your public key out to everyone, and then you just use your private key for decryption. But the reverse can also be used. There's no real difference between public and private key and how they function, just in how we store them. So I can also take my private key, use RSA plus some data and get an encryption, and then the public key plus RSA can decrypt it. So we have one form of encryption, and we have two keys. If I encrypt with the one key, I have to use the other key to decrypt. And if I encrypt with this key, I have to use this key to decrypt. Okay, we're going to try and walk through this slowly. It's kind of convoluted, so don't worry if it's seems confusing, we'll walk through it slowly, and then if you want to look back at the notes afterwards, and that would probably be a helpful thing to do. So if Alice wants to send a secure message so that Bob knows that it was her who sent it, first she's going to create what's called a signature. She takes some text. It can just be as simple as her name, Alice, and she encrypts it with her private key. So Alice's private key plus the word Alice creates her signature. It's some jumbled, encrypted bunch of text encrypted with her private key and results in her signature. Second, she writes her note and appends the signature to the end of the note. So her note is the thing that she's trying to communicate to Bob. That could be like, hey, Bob, how's it going? Any useful information. Then she encrypts the combined note and signature with Bob's public key and finally sends it to Bob. So we have her signature, she adds on a note, and then she encrypts the whole thing, the note and her signature, with Bob's public key, and she just like sends it off to Bob. On Bob's end, so this is what we have right now. The note and the signature encrypted with Alice's private key, and then the note and signature encrypted with Bob's public key. So on Bob's end, he can decrypt the whole message because it was encrypted with his public key. He has his private key. So he encrypts the whole note and signature, and now he has the note and Alice's signature. He can look at the note and he can read it. It says like, hey Bob, how's it going? So at this point we have secure communication, but he still needs to authenticate that it was Alice. So with that, he can look at this signature. Second step, he's going to use Alice's public key to decrypt her signature. So this signature was encrypted with the private key. So he uses the public key, which is publicly available, and he can get the signature, just the word Alice. So at this point, if the signature reads Alice, then Bob knows that Alice did send the message because only Alice could encrypt the signature with her private key so that the public key would successfully decrypt it. So if we're thinking of a case where I'm trying to impersonate Alice and I make a signature, I add a note, I can still use Bob's public key to encrypt the whole thing, and I send it to Bob. Bob gets it. He decrypts the whole thing with his private key. My note will make sense to him. I could be like, hey, it's me, Alice. But then when he goes to decrypt the signature with Alice's public key, it's just going to be gibberish. Because anything that I put as that signature, when it's decrypted with Alice's public key, is going to be gibberish unless it was encrypted with Alice's public key or private key. And Alice is the only one who has her private key. So if I'm decrypting this signature and it's anything that doesn't make sense, then I know it wasn't Alice. And because of this, Alex's signature can literally be any string of text that she wants. Well, as long as it like is readable. She could just be, hi there, I'm Alice, or like Toronto Raptors, or like any just word. As long as when I decrypt that signature, it's human readable, then I know the only way that it could be human readable is if Alice encrypted it with her private key. Any questions on this? So I'm going to go through it one more time, but again, I think it's something worth double checking in the notes. So first, Alice, she wants to create her signature. Her signature is her private key plus some text, in this case, Alice. We get the signature from that. Then she can add on any note to the signature. This is the communication part of it, or data that she's passing. And she encrypts the whole thing with Bob's public key. Because she knows if I encrypt it with Bob's public key, he's the only one who will be able to decrypt it. We get her signature and the note all encrypted with Bob's public key. When Bob gets this message, he sees the thing. He's like, hey, I'm going to decrypt this message with my private key. I'm the only one who can do that. I'm the only one who can securely get the note and signature. He gets the note and signature. He reads the note or data. And then he's like, okay, I just got this information from Alice. I want to make sure it's her. I know Alice creates this signature with her private key. So if I try and decrypt it with her public key, which I have, is widely available, then I should get something that makes sense. So we take her signature, decrypt it with her public key, and then if it's something that makes sense, we know it was Alice who sent it. So there's a couple things for this to like kind of work well. One of them is we can think of a situation where Eve can still maybe impersonate Alice. And this is the situation where Alice goes, hey, Bob, did you know that Alice is, or Eve tells Bob, she's like, hey, Bob, did you know that Alice's public key is this? Eve gives Bob a fake public key from Alice. And then she goes back, she creates this whole set of things using the corresponding private key to the public key she gave Bob, and she can like trick Bob into thinking that she is Alice. To stop this, and the reason we call it a public key is your public key should be like widely available. The more widely available you make your public key, the more secure this asymmetric and signature thing is. Because if I like go on the rooftops and yell like, my public key is whatever this is, then no one can come back later and be like, hey, did you know Travis's public key is like purple dinosaurs? Because they're like, no, I know it's not that because he told everyone. Like it's really hard to impersonate, you know, that information because it's so widely available. Whereas if I'm really secretive with my public key and I only give it to some people, then you could easily go and fool someone else into thinking that my public key is like purple dinosaurs or something. So if we're very public with our public key, then this form of signatures within encryption, we can achieve that thing that we were looking for. We can get secret communication where we have verified who we are communicating with.
What would that actually translate to making it publicly available?
So some people, like when this is used in messaging systems, maybe you have an API endpoint that you can just look and see anyone's public key for that messaging system. Some even bloggers and stuff allow for people to communicate with them by RSA and signatures, and just on their website they'll say like, hey, here are my keys, like my public key and stuff. A lot of the time, like we as people aren't, using the keys ourselves. It's just public internal to the application. So the client and server are very public to each other about people's public keys. And so if the server, or say the client is trying to send a message to someone using a public key, they can just ask the server like, hey, I think this is the public key I should be using, is it? And the server will just be like, yeah, that's the correct one, or whatever. Cool. So we're back with Alice and Bob. They're fresh off implementing this like RSA security. Oh yeah.
I just have a question about brute forcing. Why can't you brute force if you know someone's public key? For example, you can encrypt a message with someone's public key, and then brute force, like you kind of decode it with like random strings of like private keys. See which one matches.
Yeah, you could. But the thing behind some of these stronger encryption algorithms is their keys are like large. So if you're using like a 64 character key, the numbers on like brute forcing that are still not like within a computer's or like human lifetime at this point. So you can brute force that, and there are some older like encryption algorithms that would have like shorter keys, 16 characters, or like I think even like 32 are breakable at this point. So yeah, that is something to think about. But we're also going to look at some things you can do to counter some methods of, well, I guess not brute force exactly, but that style of security.
So does it aim at having a public key, having a key, something
Well, the signature isn't something that's being brute forced. It's the key itself. So Alice, in this case, it doesn't matter because it gets encoded or encrypted with the private key to become the signature. And with these encryptions, the signature is always, like if I take a string and encrypt it, it usually has a fixed output length for a lot of, at least this type of thing. Yeah, I don't think the length of the signature would make a difference because it's more, we're not trying different signatures against the key. We're trying different keys against the signature. So we know that this is locked with a private key, and we have the public key. So we're just using tons of combinations to see if we're getting something that makes sense with the key itself. The signature might come into play eventually, but the bigger factor is the key length. But brute forcing is also another thing that's becoming, as we go forward with computing, it becomes more and more of a risk because people are coming up with smarter and smarter ways to like brute force check things. And even with things like, I don't know if you guys know a little bit like quantum computing, but quantum computers, one thing that they're good at is just checking, like essentially brute forcing. If you have huge lengths of data and you need to check them against certain features, they're way, way faster than traditional computing. Quantum computers would suck for any sort of normal use that we would do them for, but they're really good at that thing. So there is a worry right now within security about if quantum computers become more available, brute forcing becomes much easier, and security would have to change based on that. But so Bob and Alice, they just made this RSA security improvement. But then they get some bad news, and they find out their whole database has been breached by Eve because she had information from Alice. She knew Alice's mother's maiden name and high school, and she did some hacking of her own and found out the database credentials through that. However, this time they think they're prepared. They don't store any of the messages history in their database, and all of their passwords have been hashed. They're not fools. But so they breathe a sigh of relief. But later, Bob's checking through his finances online on his banking app, and he sees that he's sent like $100 to Eve. And then he remembers that he used the same password for both StringCan and his online banking for some reason. And he realizes that Eve has somehow decrypted the hashed passwords. But how? Hash tables. So what makes you, hash tables are like rainbow tables, I think they're called sometimes. The idea of a hash table is you make a list of the most common passwords out there. And then you run it through a hashing algorithm. Hashing algorithms are, again, pretty available. And then if you have a data breach, if you have a bunch of hash passwords that you've stolen from a database, you can just do a lookup and see if any of these big hash strings match any of the strings that you've put in your hash table. And if they do, you can say, oh, I put in the input password and I got this hash, and that hash appears in their database. So I know the password that they used to get that one must have been a password. So let's try and break Bob's password. So here we have a password. We know that Alice and Bob store their passwords in their database with an MD5 hash. We can go online. We can go to an MD5 hash generator, or we can use the application directly in anything that we wanted to, and we can just put in a password and we can get the hash that would be associated with it. So that's all I did for this first one. Actually, password. There we go. So we see 5F4, and then the end of it is F99. So what do you guys think are some common passwords that would be out there? Monkey? Monkey. So I'll copy this password. What are some other common ones? 1, 2, 3. I'll copy this. What else? Admin. Keep them coming. What's like 1, 2, 3, but for letters? There you go, A, B, C. Another common one is like patterns you see on your keyboard. Yeah, QWERTY. QWERTY. ASDF. Okay. So, I mean, if we were professional hackers, we probably wouldn't be doing this by hand. We'd probably just look up some database of, the million most common passwords and then just have it run through common hash things. In fact, like, I bet you if we looked up a rainbow table or hash table for MD5, we could just download that data and get for the probably like million most common passwords or something. So we build up this hash table that we have, even with our limited number of passwords, and then we look in the database that we stole from Bob and Alice, and we see, okay, the email that's stored bob@gmail.com, and then I see the password associated with it, or like this might be the password digest, meaning that it's been converted into a hash, and we see this hash. So looking into our table, we can see that it matches with QWERTY. So we're like, okay, Bob's an idiot. He used QWERTY for his password, and then Eve can break into Bob's other accounts as she wills. One reason why we need kind of secure passwords. This is only, I know people who have like password 1, 2, 3 and stuff like that. But yeah, and real hash tables would be much more extensive than this one. So what's the solution? Well, I kind of spoiled it, but it's using Assault. When you use bcrypt, you ended up using Assault just because bcrypt incorporates them naturally. But what Assault is when we're building this hash table here, we're assuming that everyone's password is stored and hashed just as they were inputted. Assault would be the idea of every password that someone inputs, we add on a random string. So it would be this plus, like maybe our salt is, this is a salt. And then the hash we use is here. If we used the password, it would be password plus this is a salt. Any password the person inputs, we add on our salt, and then we put it through the hash table. Or sorry, we put it through the hashing algorithm. And what this does is a person can't use a standard hash table on our database now because all of their common passwords, they're just checking for them like this. In order to match password with our actual hash password, it would have to be that they some reason checked password plus this is a salt. And in real world cases, of course, our salt wouldn't be this is a salt. It would be like a long generated string. And you could make it really long, 32 bits, 64. But then what might be the problem? Like if we rack our hacker brains, what could we do if someone's using maybe a salt like this? Yeah, so if they have a salt, this is a salt, and we either look through patterns to find it, or this salt has to be stored somewhere. If we also crack the salt, and we know the hash algorithm that they're using, and we know their salt, then it's going to take more effort for us because we can't just use maybe a rainbow table or a hash table that we've created before, but we can make a custom hash table appending all of the most common passwords, the salt that we know where they're using, and we can break it that way. The other thing people do to try and like one-up that security flaw is they have like a wandering salt. So the first password that's stored uses this salt, and then the next password that's stored uses a different salt. And then for each new password, a different salt is used. But the thing with this, if it was truly random and I just stored a random salt on it, then how do I remember what salt was used when I'm like decrypting this password? So if it's password and then just a big jumble of letters, when I'm authenticating that user, I have to take the password that they put in. I have to know the salt and the thing to decrypt it and see if it, to run it back through the encryption algorithm to see if it matches the hash in my thing. So I need to know the salt when I'm authenticating them. So if we have a wandering salt, there's a couple ways to remember what the salt was. Maybe you have another database that has, or not another table in your database that just stores the salt that was used. So password, for this password, that salt was used. For 123, another password was used. For the other one, another salt was used. And so now the hackers are going to have to take it a step further. They can find this salt within our information, but then for each password, they're going to have to make a hash table. They're going to say, okay, this is the salt. I'll make a hash table specifically for this password and see if I can break it. I'll make a hash table specifically for this password and see if I can break it. The other way wandering salts are created are with random or pseudo-random number generators. So there are random number generators or random string generators where if I give it, you give it a seed normally, which is like an initial value to randomize everything. If I give it the same seed, it's going to generate the same random numbers in the same order. So it might go like 1, 2, 3, 3, 4, 5, 6, 5, 7. Each subsequent number is random in that it's not going to be like the same. It's going to be a random thing. But if I run this random generator again, giving it the same seed, it'll produce the same sequence. So the first number is that. The second number is this. Third number is 6, 7, or 6, 5, 7. If I use a different seed, it will produce a totally different sequence forever, like into infinity. But using the same seed, we'll get that same infinity kind of sequence. So the point here is not that you need to know this level of detail, but with security and things, it's always kind of like a battle on either side, and nothing is 100% secure. Although it's like pretty much impossible that someone's going to make a hash table for every password and go through all that effort, it can happen, and so you just need to think about how you can best secure your stuff given your time and given the nature of your application. Oh. Any questions on like salts or hashing? Yeah.
What are the things that you
Um,
Or are
ye-
you gonna compare it with a different
yeah, yeah, that would. I'm sure someone out there does something like that. I mean, again, it's secure as far as you keep that process secret. If it becomes like knowledge that you run it through it twice, then they can do a hash table and then run stuff through twice. It's always like that back and forth. You could have a really complex thing of set of steps that you're hashing. Like you hash, add a salt, hash again, do this, and then if that ever becomes public knowledge, then it's kind of annoying to have to do, but it's way less secure, obviously. So last case I think we're going to look at is after putting out a notice for all the users to, refresh their passwords and change all their other site passwords if they use the same one. They've added a salt, and Bob has like a frustrated call with his bank over how easy it was for Eve to take his money. He doesn't want it to be that easy for someone to log into StringCan, even if they have the correct password. What can he do to make StringCan more secure than his bank apparently was? Yeah. So two or multi-factor authentication. So two-factor authentication or multi-factor authentication is the idea that you're using multiple factors to prove who you are. And the different factors aren't just additional pieces of information. So when you go on to, like most people use security questions. What high school did you grow up in? What did you want to be when you grew up? If you just have like 6 security questions, you don't have 6-factor authentication. That's still just one additional level of a factor. A factor has to be different categories of proving for who you are. So the examples are something you know, that might be a security question, or even a password. It could be something you have, something you are. Could be your location. It could be. It's hard to think of factors after that. I know there's like. A phone, I think, is kind of considered as like something you have. So that would be, a phone is like that level of authentication. So if we're logging into Gmail and we have to provide our password and a security question, that's something you know. To make it 2-factor would be then they send you that text and you put in the number. So that's 2-factor authentication because it was something I knew and something that I have. The classic example of like 2-factor authentication is like ATMs. When I go to my ATM, I have to give something I have. I have to put my bank card in there, and I also have to provide something I know, being my PIN or my password. Yeah, if you're getting to the point where you have like a chip implanted, that's like something you are. Or it's probably a gray area between the two of these. But something you are might also be like your fingerprint scan on your phone, or like a retinal scan on phones do it now too. But if you had like a highly secure banking system, maybe you have to provide a password, you have to verify it with like a bank card or your phone, and then you have to do like a retinal scan, and then you have 3-factor authentication. Some apps use like location-based authentication. So I don't know, I think it's Gmail when you're logging on from a new location or a new computer, they'll say like, they'll make you do the 2-factor authentication by sending your phone or something because they know something's changed and they want to just do the extra level of security to make sure you are who you say you are. Google Authenticator? What that's like?
It generates like a random key.
Yeah.
And then you have to enter like that key on the website within like 15 seconds.
Oh, from the app itself, like your phone, or?
Is that considered one of the factor or?
Yeah, that would, if you have to use it. Yeah, that would be like another factor because you need to have access to that application itself. I know like World of Warcraft for a while, you could use like an app to like generate a random password when you were logging in, or they even sold like these keychain things that would have exactly what we looked at here, that like random number generator that would produce the exact. So if you went like random and you gave it a seed of 1, 2, 3, they would store their side. They knew what seed your like keychain would use, and so you'd like hit the button and it would generate a new password. And then if you put that password in, they'd run their pseudo random number generator on their side and verify that like it was you. So that's like two-factor, and that you own this like weird keychain thing. So like there's like more. Let's see, the 5 factors of authentication. So something you know we looked at, something you have like a phone, or this is exactly what WoW did. Had one of these things. Something you are, so you have like a fingerprint scanner or retinal scanner. Somewhere you are, so this is related to IP address in a lot of web applications. Could be physically when you go into a bank, you're there. Something you do. Something you do is type of authentication which provides identities by observable actions. These actions could be things like gestures or touches. Windows 8 has a feature called Picture Password. This feature allows the users to set up gestures and touches on a picture as a way to authenticate themselves. Yeah. You could have to like bring in your friend to like say, yeah, hey, this is Travis. Any questions on two-factor authentication or multi-factor authentication before we wrap up with that one? Cool. Last thing we're going to touch on is authentication can be super complex, like we've just seen. So some might argue, like, why do it yourself? There's a lot of packages and modules and things we can utilize out there to help us with authentication. One option is like single sign-on options. So you've probably seen on a lot of sites, even with Compass, you're not using that site's specific authentication. You're using another service's authentication. So with Compass, we're signing in with GitHub. A lot of accounts these days, you sign in with, you at least have the option to sign in with Google. So what would be some benefits of using like a single sign-on? If I just use Google's account information as opposed to making my own authentication on my app. Yeah, you don't have to remember a lot of passwords. Yeah, you would assume maybe that it's more secure than you could because Google's like this billion-dollar company, hopefully. Yeah, that's one thing for me too. Like if I have to sign up for if I'm using something and I'm probably not going to use this very often, and I have to sign up for a full account for them, I'm always like, I'm just not going to do that. But if I can just use Google, I'm like, sure, I don't care. Benefits, we don't have to do all the programming of setting it all up ourselves. What are some cons maybe? Yeah. If the user loses their Google account, they can't get into your service.
I don't know the mechanics behind it, but I got an email recently from, forget what, but they said that it had been hacked, but I used Google, but I just assumed that Google,
Separate?
they weren't really sharing that information, like the password wouldn't be through them, but I don't know if that's true or not. I'll have to look into it.
Yeah, they wouldn't have given their shared password information, but they would have had like your email and any other information that you had. Yeah, but also if Google now becomes breached, then your accounts on that site are breached as well. And these bigger sites are maybe bigger targets for people. They are probably more secure, but another con is it can make your application restrictive. If you only let someone log in with Google, then if someone doesn't have a Gmail account, then they can't log into your thing. It's it's probably like rarer and rarer these days, but there's a lot of people out there who are like, I don't want to use that like service, or I don't want to be part of the like monoculture or something. But yeah, there's something to think about. With when we're doing Node and Express applications, there's a really good module called Passport. They allow for, let's go to their actual site. So they can do like single source authentication. They're pretty quick to like set up. You can choose different options for authenticating: GitHub, LinkedIn, Twitter, whatever you think is the best. If that's something you're interested in, implementing single sign-on, look through their docs. They're pretty straightforward. Also do some digging around. See what's available for you out there with authentication. You can kind of ease in and out of how much you want third-party software to take care of you. You can get them to do everything. Or you can say, I just want you to take care of like hashing of my passwords with like bcrypt. Or maybe you want to do a little bit more. You want them to take care of like your whole scheme of how you store the password in your database. Maybe you don't even want to store passwords in your database. You want them to store all your passwords. There's lots of different schemes you can go into with authentication, depending on how little or how much you want to be involved in the process. But yeah, Passport's a good initial step to like check it out if it's something you're interested in.
Are you sharing, like, how much data are you sharing then with those entities? Like, if I build this and install it, like, do they just know that, I guess, where's on their end for, like, quality control and that, so they just, like,
Yeah, that's a good point. You end up putting a lot of faith in these things. I truthfully don't know too much about like quality control with a lot of these services. Something where they're just providing the interface between you and single sign-on, I would assume would be more safe because they're not actually handling any of your users' information. But yeah, maybe what's to stop them from putting a kind of secret implementation where whenever they're putting email and password into the form, they're storing that or using that or things. I mean, in general, the more common, more used ones have been stress tested by other people using them. But those are things to think of for sure.
but I guess, like, there's no restriction on that, like, their end to say that you can't use, like, Google login to, like, my Action's website. They're like, as far as they're concerned, that's fine.
To do what?
If I built like a hacking.
Oh, just like a yeah.
Saying, yeah, send me to Google. Like,
Yeah.
like they're not saying that there's no authorization process with implementing something like this, I guess.
No, yeah, they're not going to guard you from adding it. I would assume if like you were doing something like that and someone reported it to like Google sign on or stuff, they might then take action.
Yeah.
But there's no way, there's no like pre-screening process or anything like that you would have to do.
Can you do the sign on and sign up with Google, Facebook? It tells you what they're going to get as well. Yeah, yeah. But I'm just like wondering if I like on their end, if there was any sort of, like, can't use Google on your related website.
Yeah, like you're on the dark web. Yeah.
Next steps after.
Here they have job opportunities in Montreal for that type of thing. Yeah, any other questions? That's all I had to cover on authentication, but any questions on anything we went over or just like authentication in general? Cool. Yeah, like I said, it's a huge area of study, of interest. It's something you can delve a lot further into if you're interested in. But I think it's helpful in terms of the concepts that we covered in today's lecture, not to be an expert in all of them, but just to be familiar with kind of like how they work. When you hear of asymmetric or symmetric keys, kind of know what that is. You don't need to be able to like implement that algorithm or remember exactly how like this key exchange works. It's just like a good set of information to have on the back of your brain. Cool. Thanks, guys.